Hello, and welcome back to my YouTube channel. My name is Professor Govala, and today I'm going to be talking to you about two superposition examples, specifically example 1, where A says to find the I using source superposition, and the second part of the problem says to find the power dissipated at the 10 ohm resistor due to I1, I2, and I total, which is just I in this case. The second example we're going to be looking at is, again, superposition for a dependent source. So this is the dependent source right here. And the problem wants us to find Vx across the 6 ohm resistor using superposition. So let's dive into first the superposition theorem. And it says that a circuit can be analyzed with only one source of power at a time, and the result of each source is used to find the total response of the circuit. Where, for example, if we want to find V at a certain node, we first find V1, where V1 is only source A, and then on, and then source B is off. And then we find V2 independently, where V source B is on and V source A is off. And then we add those two results together to find our V total. This will become more apparent in the examples that we do, but we can do the same thing for currents as well. Same principles apply. So let's go to the first example. And we see that in order to find I using superposition, we can, again, cancel out this source right here, or make it a short circuit, and then only analyze I/O. So let me go ahead and redraw that circuit. It would look something like this. So again, we short our voltage sources, but then our current sources, we open them. And that will make that will be more apparent in the second half of this example. So again, R1 is equals to 5, and R2 is equals to 10 ohms. And we label this current that goes through here as I1. Again, this source here is 6 amps. So in order to find I1, we can use what we consider the current divider. So the current divider says I is equals to the voltage, the resistance, not where I1 is flowing. So this resistance, so 5 over the addition of both resistors. So 10 plus 5 times the current source, which is 6. So this is equals to 30 over 15, which is equals to 2 amps. If you're not used to the current divider circuit, you can do a KCL where you solve for currents using mesh analysis. So this is I1 and this is I2, or let's say IA and IB, where you say IA is equals to 6 amps. And in the loop here, doing the KVL, you would say using inspection, since this 5 and 10 ohm resistor touch the IB, we add them together, minus, this would be 5 times IA is equals to 0. So this is your first equation. This was your second equation. And essentially, this is 15 IB minus 5 times IA is 6 is equals to 0. So then IB is equals to 30 divided by 15, and you get the same thing, 2 amps, where again IB is equals to I1. So I hope this makes sense. Again, it's really good to know your fundamental equations like the current divider. But then, so we found I1, so let's go ahead and find I2 now. So I2 says that we need to redraw the circuit, but this time around, we need to open circuit this. So zero current means it's an open circuit, and then do some circuit analysis with the VO equals sync to 45 volts. So let's go ahead and draw that circuit now. We see that that circuit will look something like this. Let me get some room here. Let's open circuit on this end. There's a resistor. This is 10. This is 5. This is the voltage source. And we consider this current now I2. And essentially, we can see that this current I2 flows into the whole circuit. So again, we could write a KVL, and we could say 5I2 plus 10I2 plus, because it's going into this plus terminal, plus 45 is equals to 0. We could pull out an I2, and we're left with 5 plus 10, which is 15, is equals to negative 45 divided, negative 45. So then I2 is equals to negative 45 over 15, which is equals to negative 3. And superposition says now then that this total I here that we had from our original problem, I is equals to I1 plus I2, which then is 2 minus 3, which is equals to negative 1 amps. The way you can prove this is by saying that, let me get some room here, is by saying that imagine that we have both these systems on. What we can actually do is write two equations. We can write an equation here called I1 and an equation here called I2 using mesh analysis. So we can say that I is equals to, or I1 is equals to I naught, which is equals to, we said 6 amps. And then this is our first equation. And then we could write a KVL around I2. So then we would get I2 times 5 plus 10, or let me do it the long way, just so it's clear. I2, or we could say 5 times I2 minus I1 plus 10 times I2 plus VO is equals to 0. This, if we pull out an I2, we're left with 5 plus 10 minus 5 I1 plus 45 is equals to 0. So this ends up being I2 times 15 minus 5 times 6 plus 45 is equals to 0. This ends up being I2 times 15 minus 30 plus 45 is equals to 0. Or I2 is equals to 30 minus 45 divided by 15, which is equals to negative 15 divided by 15, which is equals to 1. So this is kind of the proof that superposition works, where again I2 is equals to I in this case, right? In this loop case, we said I2 is the same thing as I, and we get the same result. So this is kind of the proof behind source superposition. Next, they want us to find the power dissipated at the 10 ohm resistor due to I1, I2, and I. So this is simple, right? So essentially, we come here and we say that I squared times R 2 equals 10 ohms is equals to P1. So we could say power at I1. So PI1, let me just say 10 ohms is equals to I1 squared times R10, which is equals to 2 squared times 10, which is equals to 40 watts. And P I2 over the 10 ohm resistor. So I2 squared times 10, which is, so I2 squared times R10, which is equals to negative 3 squared times 10 is equals to 90 watts. And then they said they want us to find PI at the 10 ohm resistor, which again, PI is just this current times this current squared times R2. Again, I squared times R10 ohms, which is equals to negative 1 squared times 10, which we get 10 watts. As you can see, PI over from the 10 ohm resistor is not equals to PI1 10 ohm plus PI2 10 ohm. And I want you to pause the video and try and figure out why these two are not equal. And the reason why they're not equal is because the linearity property does not apply to power. For example, if we say P is equals to IV, which is also equals to V squared over R, which is also equals to I squared over R. So then we can say that, so if P is equals to IV, but V is equals to IR, so if I depends on V and vice versa, P is not linear because again, I depends on V. So if you change this changes as well in a proportional manner. As a result, this cannot be a linear, they cannot follow the linear property. So then let's go to the second example. And what I'll do here is I'll get some space here. Now that we have some room, they want us to find Vx across the 6 ohm resistor. And we know that this entire node is Vx because there's no components through it. So the Vx is the voltage across here, and the total voltage from here to here is also Vx because they're in parallel. So we can say that let's first start by shorting this voltage source and finding Vx, which is this voltage source. So let's go ahead and draw that circuit. It will look something like this. This is 2 ohms. This is 9 ohms. This is shorted, so it's just a short. This is that dependent source, 2 Vx. And this is 6 ohms. And this is 6 volts. So there are multiple ways to solve for Vx1. So this will be considered Vx1. And maybe pause the video and see if you can find out how to find Vx1, and then come back to the video and see if you got the right answer. But essentially, you can do a KCL. And what I'll do here is say that essentially the current coming in here, let's say I1, this is I2 is leaving, is I3 leaving, and I4 leaving. So KCL at node Vx1 says that I1 is equals to I2 plus I3 plus I4. Let's go ahead and actually bring this I1 to the other side. So 0 is equals to negative I1 plus I3, plus I2 plus I3 plus I4. And we get that 0 is equals to negative I1. So I1, just as a side note, is 6 minus Vx1 over 2. If we multiply this entire thing by negative 1, so negative I1 will be Vx minus 6 over 2. So I hope that makes sense. So that's what I'm going to write here. So Vx minus 6 over 2 plus V2, I2 is just Vx over 9 ohms. I3 is equals to minus 2 times Vx, so minus 2Vx, because it's going the opposite direction of this dependent current source. And then we get plus Vx1 over 6 ohms. Again, these should be Vx1. Should we have a 1 next to them? So super simple. What we can do is we can pull out Vx. So this is equals to 0. And we're left with 1/2 plus 1 over 9 minus 2 plus 1 over 6. And then we're left with minus 6 over 2. Again, let me create some room. So created some room there. So basically we can move this minus 6 over 2 to the other side, which is equals to 3 is equals to Vx. If you plug this into your calculator, you would get minus 1.22. And if you divide 3 divided by minus negative 1.22, you get Vx is equals to negative 2 or Vx1. Keep forgetting the 1. It's negative 2.45 volts. Again, there's other ways of doing this, but it's nice to see it in its entirety. So this is the hardest form, I would say. But you can use things like voltage dividers, source transformation, and other circuit analysis. But again, you should get the same answer. So the next thing we want to do now is find our Vx2 when essentially this is short circuit and this is the only power source. So let's go ahead and do that right here. And what you get is something that looks like this. So this is short circuited. Two volts, 9 ohms, 2 ohms. 2 Vx. Six ohms. And we consider this to be Vx2. Again, it's this entire node right here. And again, what we can do is we can do KCL at node Vx2. And we could then see that this is Vx2 divided by 2. Again, this is another way of doing it. Instead of writing my currents like I did here, okay, like I did here, I could simply start and say that this is my node, and I'm going to start here and go outwards. And I'm just going to add a plus, unless I have a current opposing it, like this one. So essentially what that looks like is Vx2 divided by 2 plus Vx2 minus 2, because this is this 2 volt power supply, divided by 9 minus 2 Vx, because I'm being opposed. It's going the opposite direction. Vx2 plus Vx2 divided by 6, which is equals to 0. Again, another way of doing it, which you would get the same result. But again, I can pull out a Vx2, and I'm left with 1/2 plus 1 over 9 minus 2 plus 1 over 6. This negative 2 over 9 goes to the other side as just 2 over 9. This value here is again simply just negative 1.22. This is times Vx2, and this is 2 over 9. If I divide, so Vx is equals to 2 over 9 times negative 1.22, or sorry, negative 1.22, which is equals to negative 0.1818 repeating. So this is my Vx of 2 right here. And superposition tells us that Vx is equals to Vx of 1 plus Vx of 2, which is then equals to negative 2.45. So minus 2.45 minus or plus negative 0.1818, which is equals to negative 2.63 volts Vx. And again, we can prove this. Again, if you're unsure, or if this doesn't satisfy you, you could go ahead and solve for Vx right here, this Vx, and don't short circuit any of the power supplies. And let's go ahead and do that. So if you start with Vx, again, this whole entire node is Vx, and I'm going to consider my currents going this way. All right. So I'm just going to write out the equation. It's a little bit far, but hopefully you paused the video and you have the problem next to you. So I get Vx minus 6 divided by 2 plus Vx minus 2 divided by 9 minus 2Vx plus Vx over 6 is equals to 0. I can pull out a Vx. I'm left with 1 over 2 plus 1 over 9 minus 2 plus 1 over 6. Again, is equals to, this is a negative 3, and this is a negative 2 over 9. So this is positive 3 plus 2 over 9. If I went ahead and said that this is equated to negative 1.22, as our previous results would show, then Vx is equals to 3 plus 2 over 9 all over negative 1.22. And when you do that, you get negative 2.64. Again, I'm using kind of some roundings and fractions, so it might be a little bit more precise. So, but this is essentially the same as this. All right. So I hope this makes sense. Superposition is a very, very nice analysis method, especially when you're dealing with complex, very, very complex circuits where you don't want to be dealing with a lot of power supplies. You could short one and do the analysis with others in there. And I hope you liked the video. If you did, please like my videos, share my videos, comment on them, and check out my other videos. Thank you. Have a wonderful day.